Okay, welcome to lecture 19, video number 1. We're talking about low temperature geothermal resources. So we've already talked about the geothermal resource itself. So we're now just going to do, as this first video, an overview of the technology that is used to tap into the low temperature geothermal resource. Okay, and to do that, we're going to briefly review heat pumps. I know we have a video about this from 2 lectures ago, but there's a few points that I just want to make sure are fresh in your mind at this very moment. So a heat pump, again, the point is a heat pump concentrates heat, and it does so by taking that heat from a cold space, so a cold area, and moves it into a hot space. So it moves heat in the opposite direction that you would expect, from cold to hot. You put in work into the heat pump in order to do this, so we don't violate the second law of thermodynamics. Now, when we use the actual word heat pump to talk about technology, when you say that house has a heat pump, you're saying that it has a system which can reverse direction. So most houses have an air conditioner, right, which can cool a space in the summertime. So let's draw that. Here's a house, right? And this house has some component inside, generally contained in your heater, which is absorbing heat, so it's the evaporator. So this is absorbing heat from the environment in your house, which is maintained at some low temperature compared to the high temperature. Remember, this is for summer. Okay, so, and then that working fluid is brought outdoors into the condenser, where that same energy is then rejected to the hot space. So it concentrates heat from a cold space to a hot space. It's taking the heat from inside your home, putting it outside. This is how an air conditioner works. Most of us have an air conditioner. Now, some houses have a heat pump. What that means is that the heat pump can be reversed in wintertime to exhibit the exact opposite behavior. In winter, you do not want to cool your house. You want to heat your home, right? So now our temperatures are switched. Our home is the hot temperature reservoir. The area where we want to reject heat, and it's the hot area, and the outside is now the cold area. We have the same components, whereas before this was the evaporator, and this was the condenser. It is now opposite. This is the condenser, and this is the evaporator. And how we accomplish this is we have all the same components, including a pump and a valve and 2 heat exchangers, but we've actually reversed the direction of flow using just some basic equipment inside the heat pump itself. And what that does is it reverses the direction of heat flow from going out to now coming into the house. So when you say heat pump, like that house has a heat pump, this is the technology we're talking about. Okay, the performance of a heat pump is quantified with the coefficient of performance, which we just call the COP. Okay, and this generally is given as a range from 2 to 6. Those are kind of the expected values. We'll break down how to calculate this depending on, again, what we're doing. Are we cooling a space or heating a space? So in summertime, we talked about the Carnot heat engine. Well, there's also a Carnot heat pump, which we can find the coefficient of performance for. That tells us the maximum coefficient of performance we can get. So for cooling scenario, the temperature of our low space divided by the difference between the temperature of our hot and low space tells us our theoretical best coefficient of performance. The higher it is, the better we're doing. Please remember, because we have temperature by itself here, not a delta T, we have to use Kelvin. Must, have to. Of course, this is the COP for a Carnot heat pump, whereas a real heat pump, we're going to quantify the coefficient of performance like this. The cooling load that we are producing on the house, so how much heat we're removing from the home divided by the amount of work we have to put in to produce that cooling. In the wintertime, when we are in heating mode, now we care not so much. Remember, when we are cooling, this was the temperature we cared about, right? Because the house is the TL, as we showed right here. In wintertime, the house is at TH. So we're going to say TH is the thing we cared about, divided by the difference between TH and TL. So in heating mode, that is the definition of the Carnot COP. That tells us the best we could do using the best heat pump. In reality, a real heat pump, we define the coefficient of performance now as QH, because we're heating mode, so QH is what we care about, that's what we want, divided by work in. Okay, so just a note about COP. So the coefficient of performance, sorry about that. So the COP, the COP will quantify, it quantifies exactly how much heating or cooling, whatever you're trying to get, you get per unit work. So if you put in 1 kilowatt of work, because in order for a heat pump to work, you have to pump a working fluid, so that takes work. If you put in 1 kilowatt of working fluid, of work into the working fluid, and if your COP is 5, then you can expect to get 5 kilowatts of heat, which is 4 kilowatts of that will be heat we took from the cold space and moved to the hot space. 1 kilowatt of that heat will be the energy that we added into the pump, which was put into the fluid and then rejected as heat into our hot space. Kind of cool. Okay, let's just do a quick example. Oh, I'm sorry. We're gonna do an example to demonstrate now a ground source heat pump. So the heat pumps we discussed in kind of our first lecture on heat pumps were air source heat pumps. So, and the ones I've been showing, we have our, if we're, let's say, in heating mode, so we have the outside is at 0 degrees Kelvin and the inside of your home is at 0 degrees Celsius. That would be bad if that was Kelvin. And the inside's at 20 degrees Celsius. And so we're in heating mode, so we're putting in heat here and then rejecting heat here. Okay, so if our evaporator right here, which is taking in the heat, is above ground, exchanging heat with the air, then let's calculate our coefficient of performance for a Carnot heat pump operating between these two temperatures. So since it is in heating mode, we do TH in Kelvin, so 293 Kelvin, which is equal to 20 plus 273, divided by TH minus TL, so 293 minus 273. 293, 273. We went from Celsius to Kelvin. Okay, when you do that math, you get 14.6. Again, that's ideal. All right, now, so that's if we're exchanging heat with the air. And because it's 0 degrees Celsius, it's a pretty cold winter day. Not even that cold, though. It gets much colder during the winter. Now we're going to try something different. Instead of exchanging heat with the air, we're going to exchange heat with the ground. So here's our condenser again, which is rejecting heat into our heated space, which is at 20 degrees Celsius. But then instead of absorbing that heat from the air, we're going to use pipes that are buried some distance under the ground. And so the ground is going to put heat into this working fluid, which will go and exchange that heat with our heat pump. And the temperature of the ground is going to be 10 degrees Celsius. In the wintertime, the ground is much warmer than the air. You know this if you go into a basement or dig a really deep hole or go into a cave. Even it feels warmer than the air. Okay, so now if we do our Carnot heat pump calculation for these new temperatures, then we get 293, which is 20 degrees, divided by 293, now minus 283. And that gives us a COP of 29.2, which is double the COP when exchanging heat with the air, after just a difference of 10 degrees C. So the ground, at least several meters below the surface of the ground, as we talked about in our last lecture, maintains a temperature at average air temperature, averaged over the year. Which is great because on the coldest winter days or the hottest summer days, that ground is at a much better temperature. In fact, the ground is going to almost always be closer to the house temperature. What this does is it decreases the lift that the heat pump must produce, where lift is defined as the temperature gradient it's working against. Remember, a heat pump is moving heat against a temperature gradient. The larger this is, the less heat it can move per unit work, and the COP goes down as the lift goes up. So the smaller our lift, the better. So what this means is on a cold winter night, we can expect the COP of an air heat pump exchanging heat with the air to be from 1.7 to 2.5, whereas the COP for a ground heat pump is going to be between 3 and 6, more than double, which means you need half the work to get the same amount of heat. Okay, there are a few disadvantages of ground source heat pumps, which we abbreviate to GSHPs. And that is the ground is solid, so your heat transfer is less effective. You're going to need more tubes, more heat transfer area to dump the same amount of heat. And as you put heat into the ground, which doesn't conduct heat very well, the ground temperature actually changes slowly over a period of years, which means by the end of your system, you're going to need more tubes in the ground than you did when you started. All right, let's talk about different types of ground source heat pumps. Okay, so we have our first one, an open loop water source. Okay, when we use the word open loop, what we mean is the working fluid in our ground heat exchanger moves in and out of the tubes. It's honestly easier to just draw a picture. So here's our house, and here we have some groundwater that's under the ground. And so we've drilled a hole, a borehole, down into the groundwater, and then we've connected that to our actual heat pump. And so we actually pump water out of here, and we put cold water in, and that exchanges heat with the heat pump and then comes out as hot water. So you see how water is actually entering and leaving our pipe. So that is an open loop. So, oops. So groundwater is pumped in and out of our heat pump. This is sometimes called a standing column well. Okay, let's look at another class called closed loop water source systems. When we say water source, we just mean that water is the working fluid inside the actual tubes running through the ground. So closed loop, unlike open loop, is when the fluid is always contained in pipes. Okay, so going back to open loop, you see here's water, and this water is going to be pumped in and then released back into the groundwater. In a closed loop system, if this is our house, we have our inside, say, condenser if we're in heating mode, then it's going to be connected to some tubes which run under the ground and form a complete closed loop. So water will circulate through this tube and then go back, and it never actually enters the ground. Okay, the one I've sort of drawn here, not necessarily, we might call a vertical. So there's two types of closed loop. There is a vertical closed loop where the pipes run vertically and they go quite far down. These we often call downhole or borehole systems. And what that generally looks like is we have the ground and we drill a hole called a borehole, which goes down generally quite far, 150 to 300 feet. And in that borehole, we put a pipe that goes almost to the bottom. And then at the bottom there is a U fixture, and that pipe then comes back up. And we then put, depending on what mode we're running in, cold fluid in one end of that pipe, and then the ground, as that fluid runs down and then up, exchanges heat with that fluid such that hot fluid comes out. Okay, so that's a downhole system. We also have horizontal closed loops. So that was a vertical closed loop. You can have a horizontal closed loop, which, as you could imagine, is cheaper, about half the cost of drilling really deep holes and then putting pipes in. Also a little bit less effective per unit depth, per unit area of length of pipe. Okay, so in a horizontal closed loop, we go down some length and then we move horizontally and then return. And so we can have kind of two ways. We have here, as I've drawn, pipes that are horizontal in a looping pattern. Right, as shown here. So if we look at it from kind of looking down on it, we have kind of this, I believe we call it a slinky pattern, where our pipes are laid at the bottom of a trench. So here's a trench we dug. We laid our pipes on the bottom, then we filled that back up with dirt. So that's one way. Or we could have a snaking pattern, where looking down on a house now, so we're above the house looking down, we've dug several trenches, and we just come out and we lay the pipes straight without doing kind of our slinky effect that we had here. So we lay those and then we bring them back. Okay, so we can have this looping or a snaking pattern. There's one more closed loop system that we should talk about. That is a closed loop surface water. water on the surface, especially near the bottom, is also really good at maintaining a temperature that doesn't vary quite as quickly as the air. So if we have some body of water that's really close, then we can put our heat exchanger just at the bottom of that body of water. Kind of like a slinky pattern, just a tight twist of copper wires. Tubes. Okay, and now I want to talk about all of these systems. I've kind of just drawn here these tubes leaving, but what I want to make sure we understand is that the heat pump, so here's our heat pump, right? We have a compressor, and then the fluid leaves the compressor and enters, let's say this is the evaporator. Which goes into an expansion valve, and then it enters the condenser, and then goes back into the compressor. And we have our refrigerant in our system following this pattern, going through our cycle over and over and over, and heat is leaving our condenser. Now we need to traditionally we would be putting heat into this evaporator, right? But how are we going to put that heat into the evaporator when the heat is like 150 feet underground? So if this is the ground, then we have a separate loop, kind of like what we've been talking about, that brings that heat to the evaporator and then exchanges heat with the evaporator. So the evaporator is actually a heat exchanger, where the working fluid here is going to be refrigerant, and the working fluid here might be could be water. I mean, there's a variety of fluids you could use here. And so here now we have some sort of heat exchanger, which is what I've been drawing here, our heat exchanger with the ground that is exchanging heat with the ground. And so this we call the ground heat exchanger, which we abbreviate to the GHX. Okay, and I bring this up because we also have what we call a direct exchange system, which is where here, let's draw our heat pump again. We have our turbine and our expansion valve and our condenser, and we have refrigerant running through these lines. Now, instead of our refrigerant exchanging heat with another fluid which runs through the ground, we actually put our refrigerant directly into the ground. So this is the ground. And we just put that heat from the ground directly into the refrigerant, as opposed to in our previous system where the heat from the ground enters our ground heat exchanger, which is then transferred into our refrigerant in the evaporator. Now in a direct exchange system, we put refrigerant directly into the ground, which is great but uses a lot of refrigerant, so not always the best idea. Okay, a few last items. Ground source heat pumps we're not going to actually classify as renewable energy because we're just heating, right? True, this can replace something that uses fossil fuels, but it's not really renewable because a fluid must be pumped in order for it to work. Now, it is possible for that pump energy to come from renewable sources, so it can be sourced renewably. Okay, but that being said, the EPA has said that ground source heat pumps are the most energy efficient, environmentally clean, cost-effective system for heating and cooling. So they get a check mark for being great. All right, let's talk about design rules of thumb for designing our ground heat exchanger, especially for closed loop systems, horizontal and vertical. How many pipes do we need? How deep do we go? Etc. That's what we're going to talk about in this next video.